Good afternoon, everyone, and welcome to our fourth and last webinar in this series. Today, you will discover how to assess the failure probability and predict the lifespan of your electronics product. But let me quickly introduce myself for those that might do not know me yet. My name is Lisa Sitar. I'm a marketing officer at Infinite Simulation System and a moderator of today's webinar. So let's begin. First, I will give you a quick instructions on the webinar tool you're currently using. As you can see, you have different options. You can minimize or maximize your menu. You can choose for a full screen mode. Please know that this webinar is being recorded, but you will receive the recording together with the presentation slides after the webinar. Regarding the questions, please feel free to ask, but not by raising your hand or trying to unmute yourself because this is not possible. Just write your question down under the question tab that you see below on the screen. We will provide answers at the end of this webinar, or in case if we run out of time, we are gonna send you the answers via email together with the webinar recording. Today, I'm joined by my colleague, application engineer Odysseas V, who will tell you more about how you can assess the failure probability and predict the lifespan of your electronics product by using ANSYS simulation tools. But looking at the agenda first, Odysseas will be the main speaker today, but I will give you a quick introduction on Infinite Simulation Systems, just in case if you do not know us yet. So Infinite, we are ANSYS Elite channel partner in the Benelux region. We are active in computer-aided engineering for already 30 years now, located in Netherlands in a small city called Breda. You can also see our office in the picture. By mentioning the broad product portfolio, we mean that apart from the electronics, we are active in many other domains, such as fluids, mechanics, optics, and much more. Besides, ANSYS simulation solutions are applicable across various industries and applications. Our main goal is exactly improving your design efficiency, but keep in mind that that's not everything we do. We also provide consultancy, we provide trainings, theoretical and practical ones, when you can really learn how to use those ANSYS simulation tools. So everything I just mentioned, you can also check on our new website, which was launched 3 months ago. So please feel free to scan this QR code and check more about anything that is in your interest. So now we are starting for real. I'm giving a word to my colleague Odysseas.
Thank you very much, Tisa.
Yep, go ahead.
Yes. So thanks everybody for joining on this last webinar session. Give me a second. On this last webinar session. And yeah, hopefully we will make your lunch once again more tasty. I want to start by saying that traditionally businesses have a design, build, test, break, and fix design cycle. And this is the traditional approach of how businesses were conducting businesses all this time. However, such an approach can be expensive and time-consuming. Furthermore, design rules and best practices may not provide engineers with enough guidance to properly design modern, cutting-edge products. By using simulation, virtual models and prototypes can be created and simulated, giving engineers more freedom via virtual testing. This will help engineers to have better insight of their design, but also give a higher degree of confidence that the physical tests they will run in the future will be successful. If simulation is used as a design tool early in the development process, it can greatly benefit and cut costs. Here in the graph, you can see that with the traditional approach, the problem can only be detected when there is an actual prototype. And to resolve them in this phase, it can be 100 times more costly, but also very time expensive, let's say. If problems arise even later in the development phase, the cost will increase exponentially. Working with simulation tools early in the design phase, engineers can predict issues and work on solutions or changes very quickly without the need for an actual physical test. This also shields out problems that might occur very late in the development, which, as we said, will be very detrimental in costs. Now let's take a little bit about electronic design challenges. Engineers today must address a wide variety of design requirements when designing electronic systems. These range from electrical, such as signal and power integrity, thermal, such as in the implementation of optimal cooling strategies, or mechanical, the ability to withstand thermal cycling, shock, vibration, etc. Furthermore, products are expected to meet lifetime requirements to ensure that they meet their intended function for at least a very big amount of time. Engineers also need to consider the effect of manufacturing, transportation, and product operation as part of their design process. ANSYS provides a suite of tools and workflows that address a wide range of electronics reliability concerns. Each aspect, electrical, thermal, mechanical, multiphysics, plays a key role in the understanding of how electronic systems operate and perform in a variety of applications. In this webinar series, we already have done 3 webinars on different reliability subjects. First, we started with signal and power integrity. Then we talked about EMI, EMC reliability. And in our 3rd webinar, we talked about thermal reliability. In this last webinar, we will be talking about lifetime predictions. Of course, we can provide you with all of the webinars and the slides if you wish to do that. So let's take a look a bit at the lifetime reliability. Lifetime predictions of products can be very challenging and cannot easily be based on experience or know-how techniques. This is of course due to the ever-expanding complication of electronic devices. The most reliable way to predict is with means of rigorous physical testing on prototypes. This, first of all, is a very costly, but most importantly, a very time-consuming test to perform. For example, a powered thermal test cycle can last up to thousands of hours before we have the first results. And if the results are lackluster after that, we need to again prototype and redo this test. So you can understand that not only the costs, but the time constraints can be great for this. Since we want to deliver a viable product with a long lifespan, these physical tests are required, and there are many compliance standards to be filled and be done. So also, this is something to take into consideration. On top of that, warranty claims on products can be extremely costly for your business, so cutting this down can be very important. When we talk about electronics reliability, and especially lifetime reliability, some of the failure mechanisms that we typically see are listed here in this graph. As you can see, the majority have ties to thermal, vibration, or humidity issues that cause electronics to fail over time. Vibration and thermal can cause 75% of failures, and mainly fatigue plays a very big role here, fatigue over time. Also, overstress with extensive board bending or sudden drops can also cause failure. Today, we will be talking a bit about all of these kind of failure mechanisms. Let's take a closer look at thermal issues, in which we talked more extensively in the previous webinar. However, this time I want to see them from a lifetime perspective. With the thermal expansion coefficient changing with the rise and fall of heat, we can have solder joint fatigue. So during temperature cycle, a solder joint connection expands and contracts. With many consecutive cycles, this can cause degradation of the connection and thus failure of it. This was a very big issue with Microsoft's first gaming console, leading to a whopping 40% failure rate of their first model iteration. A very, very, very big amount and a very big expenses in warranty claims back at the day for Microsoft. Solder joint fatigue is one of the leading causes of PCB failure. So solder joint fatigue is mainly caused due to repeated exposure to temperature changes, which happens naturally either via the on-off operation of the device or the thermal changes in the environment that the device is. This exposure causes cracks to form on the solder, and with repeated cycling, this damage accumulates, leading to further fractures into the solder joint and eventually to failure. Many things impact the solder fatigue: the maximum and the minimum temperature of the temperature cycle, how long it's staying at its minimum and maximum, the electrical properties, the material properties of the PCB, etc. Having a good understanding of an electronic system electrical, thermal, and mechanical performance under various conditions is important. However, reliability physics analysis, as it is commonly called, tells us how a product is expected to last under such conditions. Tools like ANSYS, which I will be talking in a minute, can be used to determine the time to failure or cycles to failure for all the components on a device and on a PCB using various built-in reliability models. So let's take a look at ANSYS as I talked before. ANSYS is a reliability physics solution that helps you predict product failure early in the design process, quickly and accurately. Serlog solvers are based on physics and are not design rules or past data, just purely physics. This will help you mitigate mechanical, manufacturing, and thermal risks. Serlog is a tool that it's meant to be quick and easy to use, and one of its main capabilities is that it allows us to pre-process MCAD and ECAD files and quickly bring out the model without us, the user, needing to actually make it ourselves on a CAD environment. As a result, Serlog will spit out a mean time to failure of the product by accounting for all of the different risks: vibration, solder fatigue, and we will see more later. Serlog can be used and help with initial part selection, of course. You can quickly access which part will have a better lifetime for your design and maybe change a part that you already have on a previous design just because of costs and same efficiency. It can also greatly help with quick checks for part placements. Maybe you have some natural vibration on your board and you want to check where each component is optimally placed to avoid issues due to this vibration. Choosing the final layout and bill of materials, we might also need to ensure that we have designed for manufacturability, and Serlog can help us with that as well. There is a plethora of analysis you can do in Serlog. There is thermomechanical, through-hole fatigue, vibration and shock analysis, in-circuit testing, and of course, solder fatigue analysis. The tool has more analysis not listed here, such as maybe thermal derating, trace modeling, and many more. As mentioned before, Serlog basically gives out a single result, and this result you can see here on the graph. It's the mean time to failure per component or for the whole board. We can set up profiles for all the analysis that we talked earlier. So a profile for solder fatigue, a profile for thermal cycling, a profile for vibration, etc. And see with this profile, what is the probability of our PCB, of our whole PCB, or of a certain component to fail. So here in the picture, for a vibration profile, this is with the purple line that we have set up, we see that our product has a 10% possibility of failure after 6 years when applying this vibration profile. On the other hand, for a certain thermal profile that we have addressed, here with, you can see with the turquoise color the result, we have a 10% possibility of failure after 6 years. Combining all of the different risks, we see that with the red line, this is the overall product combined risk with all the different profiles. And so we can see on the red line that our board has a 10% probability of failure after 4.5 years, more or less. And of course, this is for the whole board, but we can also see results for components individually and see which components are critical in our design. As mentioned earlier, Celloc has a very low skill level ceiling. It's meant to be very easy to use. We just need to feed it with an accurate ECAD or MCAD data, and it will automatically recognize all of your components, if not all, most of your components. It will immediately see different materials, laminates, etc. And then it will make a model of your board in a matter of minutes. Celloc also has a very rich library of close to millions of components with data tables and specifications coming straight from the manufacturers. This library, of course, is constantly updated by ANSYS, but also if you have a more exotic component yourself, you can add it to the library and you can easily change its specs and add the data that you want for this specific component. Here we see a very simple example. So we have fed Serlog an NICAD file, and it generates this 3D model that you can see in the picture immediately without any input from us. And then we input the shock profile that you see here on the middle picture. And this is the profile of shocks that we want to be testing this board. With only this input, we can see the results of the lifetime expectancy of all of the components in a table format, as you see down on the left picture, as well as the lifetime prediction curve on the right, or even displacement plots with 3D graphics on the top right corner as well. So very simply, we just put out the model, put out the ECAD model, made the profile, and immediately we get results. One other area that Serlo can greatly help is testing out different what-if scenarios. This gives the designers a lot of flexibility and enables them to make trade-offs and important decisions. Maybe a different package type for capacitors is a viable option to reduce costs but keep up the lifetime reliability. You can test this with Serlo. Or maybe you have a new manufacturer that works with different laminate. How would this affect the lifetime of your product? You can check this in Serloc. Serloc can give you the data to make important decisions for your design very early in the process of designing. Let's now check a small case study which showcases the usage of Serloc. So let's say we need to make a design decision on where this system on chip package will go on our board, both for electrical and thermal behavior, but mainly to withstand shocks. The shock profile for this example is 30G for 50,000 times. So our board should, this system on chip should withstand 30G 50,000 of times. So where should we place as designers the component? Is it better suited for placing it on the top, on the bottom, or in the middle of the board? We can bring the ECAD file to Serloc immediately and input the shock profile of 30G for 50,000 times, and we can get results immediately. So here are the results. If we place the component in the center, we see that there is a 5% chance of failure in 2 years and a 20% chance of failure in 3 years. So placing the component at the center, we can see that withstanding this shock profile is not likely, or at least withstanding it for a long period of time. So now we need to make a decision. Maybe we should place the component in a different area. As we can see here, if we place on the left picture, if we place the component a little bit more to the left and not in the middle of the board, and still apply the same shock profile, we now have a 20% possibility of failure after 9 or 10 years, and only 5% possibility of failure after 5 years. An incredible improvement with just moving on the system on chip to the left. But maybe another design decision or what-if scenario, let's say, would be to add maybe some mounting points on the board, as you can see here in the middle picture. If we add the mounting points where the dashed lines are, and keep the component and the chip, keep it in the middle, we still see that with adding these mounting points, of course, we have way less probability now of the component failing because we added these mounting points. If we want, we can also test that a scenario with an underfill, as you can see on the right hand side. So by adding an underfill to this component and placing it in the middle of the board, we see that we no longer have we have an almost 0% chance of failing due to this mechanical shock for the component. So we can, as you can see, we can very easily play around and see what's going on and on our design and make important decisions with the data that we have from Sherlock. I lastly want to touch on the subject of multiphysics and coupling with other solvers in the ANSYS portfolio. As we have discussed about different types of softwares during this webinar series, Sherlock will always have one or two-way coupling with all of the softwares that we talked and with a lot of other softwares in the ANSYS portfolio. So for example, we talked about HFSS, IcePack, mechanical, SI Wave in this webinar, and these all can be coupled with Sherlock for an in-depth simulation analysis of your whole design in different physics. Unfortunately, I do not have more time to get more into the details of this, but please, if you're interested to learn more about multiphysics and co-simulation, do not hesitate to contact us. Lastly, I want to just have a small recap. So what is Sherlock? It makes it easy to have a finite element analysis. It makes it easy for us to process things, process results, process data. It's very user-friendly. It communicates quality and reliability throughout the electronic supply chain. It will reduce your warranty returns in the field if you use it successfully. And most importantly, it will help with avoiding redesigning and retesting of your boards and your products due to failures. Thank you very much for joining us in this four webinar series. This has been the end. Hope to get your questions and also anything else you want to be discussing. You can always contact me. You have my contact details on the slides. Thanks again once for your time. I will be giving my microphone back to Tisa now.
Thank you, Odi. Thank you everyone for joining this webinar. Before we finish, I would like, as already Odysseas mentioned, share with you some contact details. So in case you come up with any additional questions after the webinar, or you have any thoughts or questions about our trainings, anything related to the topic, please feel free to ask. You can also scan this QR code to follow us on LinkedIn, where we publish and announce all the upcoming webinars and other events. Unfortunately, we do not have much time left for your questions, so you will receive the answers via email together with webinar recording and the presentation slides. You will receive that before the end of this week. So thank you very much. Again, that was our last webinar in this series, but don't worry, we'll come up with more topics, more interesting issues we need to solve together, and we'll let you know. So once again, thank you very much, and
Thanks everybody.
have a nice day.
Have a nice day. Bye bye.
Bye.